As promised in the previous mini lecture, I'm just going to go through a couple of practice problems here so that you really get familiar with the kinds of mechanistic stuff you need to know for Chapter 18. So let's get started. I told you should work through the mechanism for this. Let's see if we can't do that here. Alright, so acid, H+. Where is it going to protonate? I don't know. I think we'll have it protonate here. It really doesn't matter which one gets protonated because they're all going to get protonated. So we go from there, and now I'm just going to abbreviate wildly. So that's just going to become R. And this is obviously positively charged. This is our methyl group. And once I've done that, again, as always in this chapter, under these conditions, we're talking seriously polar protic. So it certainly stands to reason that that leaving group would leave, particularly because it's going to give me a very stable carbocation. Look at that tertiary. And, oops, I think I've got a few too many atoms here. Okay, let's erase this and get this straight. CR, there we go. Look at that. It's not only tertiary, but it can be stabilized by resonance. Love it. So stabilization-wise, show a little resonance delocalization here. Well that's interesting. Looks to me like I'm really almost to my ketone, aren't I? Very interesting. Okay, well now what do I do? Well, the thing is, there's a million different things you can do. What I'm going to do is change to a new board so I can continue this mechanism. So, I'm going to erase all strokes and continue on here. I had something wild looking like this funky positively charged ketone. What? Well, no, this is all fine. In fact, I can draw another resonance contributor here that shows what we already saw. Okay. And we're under aqueous acidic conditions. What could happen? Well, I've clearly got a fantastic electrophile in a beaker full of lots of water. I think we're talking nucleophilic attack. There we go. If I do that, then I've got this going on. And CHR, OH. Okay, now what could happen? Well, I'm not going to have room to show it, which I should, but basically whenever you see a protonated oxygen, you're going to want to deprotonate it. So, next thing is, let's see if I can squeeze it in there. I bet you I can. There's a nice long OH bond. I think I'll use my water to deprotonate that. That gives me this. Okay, now what? Okie dokie. Well, what am I trying to get to? I'm trying to get to kicking out a good leaving group and regenerating my ketone, like so. So, I think the next logical thing to do is protonate somewhere to make a good leaving group. And that would take me to this. And then I can push this guy out. That is going to take me to this guy. Well, wait a minute. Let's make it more obvious. Make it fit in with what we drew on the previous slide. So I've got that plus okay. So here is my diol slash alcohol that I was using to make the acetal to begin with. And what happens next? Well, that's pretty easy. All I have to do is deprotonate to make my ketone. So here's my ketone. Here's my alcohol. Those two go together to make the ketal. And what we've just shown is the hydrolysis of the ketal to regenerate the ketone and alcohol by addition of a large excess of water. Alright, so that was the mechanism for that guy. How about these? Well, okay. It's very similar, right? I have the same kind of ketone and I have a similar diol. What's going to happen here? Now, I'm going to think mechanism without actually drawing the whole darn thing. But basically, I know this is going to get protonated. And it makes sense that that's going to react with that. So, ultimately, I think what I'm going to see is my carbonyl carbon here is going to have those two oxygens attached. And my carbonyl carbon has two methyl groups attached. So CH3, CH3. And what do I know about my diol? Well, I'm going to end up with an acetal, ketal if you want to be persnickety, which sometimes I like being persnickety. There it is. Because my diol is attached to a cyclohexane ring. So I just made a ketal by the addition of presumably a large excess, or at least an excess, of the diol and a catalytic amount of acid. Okay. Next, how about this guy? What's the product here? Holy moly. Well, obviously I've got a protonation going on, and certainly I can protonate here. If I do that, I get this, and it makes sense that that would leave. I'm good with that. Okay. But then I'm kind of stuck. Because what can happen? Well, the only thing that can happen is the reverse step. I mean, I just don't see anything else happening here. Okay, so dead end. How about we try protonating on the other oxygen? Okay, if I do that, OH, okay, then I've got that. All right, now let's lose this leaving group. Okay, no problem. That's not too bad. COH plus H. Let's draw a resonance contributor. I like that. Draw a resonance contributor. HO. Hey, there's my carbonyl carbon. Oh my goodness, what do we have here? We have an intramolecular acetal. You can tell it's an acetal because of the hydrogen attached right there. So basically all I have to do is deprotonate right there, and here is my ring opened form of my acetal. So this is a really great example for biochemistry because this is a very simplified model of a sugar. And sugars are basically hemiacetals and hemiketals in equilibrium with one another in a big way. So being able to recognize this carbon, the carbon that is bearing both of those oxygens, that's your carbonyl carbon, that is, in biochemistry speak, that is your anomeric carbon. And we'll talk a little bit more about that so you make sure you can recognize those in sugars. So that's it. Those are the two examples I wanted to go through. This was totally optional. I hope it was helpful, and we'll see you in class.